Okay, any comments for the good of the order before we get going? I think this weekend, this Sunday is our deadline, as you'll get your notification at midnight tonight. I don't send it out myself at midnight, way past my bedtime. Actually, not always. But the next thing due is an outline, table of contents, if you like, for your presentation. So I don't know how people want to do that. I'll tell you up front, I don't. I've told you already that my idea of doing these incremental components is to get you moving rather than for me to give you any substantive input. I know that when I make presentations, with my career of the things that I've done, I probably have a bank of about 500 slides. And when I go and give a presentation on something, I make a slide that is the outline for the whole thing, and then that's what I work on to pull in the right slides to make the story that I want. Doesn't change very much after a while, but this is perhaps new for you, new material for you. But a one title page slide with an outline on it. Well, I can show you what I do. Don't want that. I didn't actually prepare to do this, but you can see my whole life. I don't know what to do. Not all of these have PowerPoint presentations in them. The ones I know would be yeah. So a not unusual thing for me to do is this is the slide that I put together when I'm making a presentation. Some of them repeat, but some detailed outline of what you want to say. This is perhaps not a bad thing. So that might be the way you want to transmit what you're doing. You might want to write it just in as the text in the text box. My comment of saying that I'm not going to chase you about this is merely to say that I probably shouldn't say it before you do it, but you should be doing it for yourself, just to get yourself organized. Getting the outline of a presentation is usually the hardest thing to do, just in terms of being able to get your thoughts together to tell the story you want to tell, and finding the material to pull into that is not. Or you may use AI. Who knows? You may use ChatGPT to do it. Doesn't matter. So, by way of background, so that's today. I guess in 2 weeks' time after that, then some kind of presentation is also due. So you know from the filling in that table of contents. And so if you want to chat about it or feel you need to chat about it, then I'm happy to chat. Not off topic, but not completely off topic after the kind of introductory things that we said today. This was an article in Science magazine, Nature magazine, Counterpoint of Science today, which I thought was kind of interesting. I guess it might. Does it work? It worked before. Worked in my office. Yeah, perhaps it's not going to work. Oh yeah, it's working. It's I guess the title you see, Can Clean Energy Revolution Save Us from Climate Catastrophe? So if you follow these things, we must be close to 1.5 centigrade already, and so that target's gone. And 2.5 is the other kind of milestone not to go across. And so this is just examining where we are. Electricity generation in terms of terawatts, yeah, in this class, I said 10 to 15 terawatts, and that seems to be what it is. It hasn't changed very much, and that's how it's mainly made up. I guess it's more than that because that's individually. There's no total on this. So 10 terawatts on coal, 6 on gas, natural gas by the looks of it, and a couple on nuclear. So it's more than 15 terawatts total. And I guess they're making the point that renewables, I don't know if that's in terms of capacity, not necessarily availability, because of course dispatchability for renewables is important. The solar panels on our house haven't been making much electricity the last 2 weeks with the snowpack on top of them. But it's interesting that it's been overtaken by renewables. I guess the interesting thing about these two plots is these are fossil fuels versus renewables, but there's also a downtick. So the big news as of a couple of days ago that China emissions had peaked and already gone down. There was an agreement between Obama and Xi Jinping to peak by 2035, and so that's great if they're going down already. Penetration of renewables in the marketplace, big in China, quite interesting. Oh yeah, so I guess this isn't CO2, this is actual electricity, sources of electricity. Global energy investments, I guess without fossil fuels, this is the money that's being put in each year into energy production. Not changing much for fossil, maybe level, right? Blue is the fossil fuels. So it's becoming it's not being banished to the hinterlands. Certainly fossil fuels are still there. Global energy generation, I guess renewables, solar is down here. Hydropower is down here. Geothermal, you'll note, is not even on the map, which is interesting. It's of the order of some of these smaller ones. It's less than hydro, so that's also small. And by far the largest is coal and oil and natural gas. So these are all fossil. And these are in exajoules. So we talked about the capacity, the global capacity was something like 500 exajoules. The US uses a fifth of that, 100 exajoules. So this is saying that that number is roughly correct. It's a ballpark number. CO2, the Western countries have peaked and are going down by the looks of it, right? The US is this blue, right? So holding steady. EU is reducing, no doubt about that. Big programs in the EU. Shipping, United States. India, I'm surprised, is small because they have a lot. They generate lots of their power by coal. I'm surprised it's so small. China's huge, of course, and the rest of the world makes up the remainder. Whoops. And this is to date emissions, projected emissions based on that. As I say, China just peaked and started going down. I think this next one that comes up is commitments that countries have made going down. And the sobering reality is these other two that now come, which are the 1.5 and 2.5 pathways, 2.5 degrees centigrade pathways. This is where you need to be for 2.5, for 1.5, and this is where we are, and the projections of those. So I won't make any commentary on it, but that's just interesting. Cost of generation, that's of course, we all vote our pocketbooks, and of course your choices of energy supply are also in line with that. But this shows that the costs of wind, both onshore and offshore and solar, are coming down. They're now kind of on par or cheaper than fossil fuels. Intermittency is still an issue, and the only way you deal with intermittency would be by battery storage, but people have also talked about thermal storage for solving the intermittency problem, that you only make solar power when the sun shines and wind power when the wind blows, and you have to fill in somehow. You have a surplus in some times and you have to deal with, store, and you have to draw on that storage at other times when you actually need it. So that's it. I just thought that was an interesting thing to kind of put the context into what we're doing. So, all right. Yeah, okay. I was looking today, I couldn't realize how bad my handwriting is in some of the slides that we look at. Look at this. This is pristine compared to some of the other things that we've seen, which are scrolled on, of course. Maybe these other notes were kind of made in COVID, so I'm not sure why they're kind of so scrawly as they are a little bit. But we're making the case for fluid flow models, and trying to make the linkage to power recovered from reservoirs, thermal power, thermal energy recovered from reservoirs. The first part of dealing with that was making sure that the reservoirs would be sustainable in terms of the fluids that are recovered from them. So, in summarizing what we talked about last time, these are the summarized notes that I put together. You don't have these, they're not in the notes. We made the point that enthalpy as the sum of internal energy, thermal energy, and pressure, if you look at each of those components, the sensible thermal energy is huge compared to the pressure change. So we're not looking at harvesting geopressurized reservoirs. So some people have looked at overpressured reservoirs in the Gulf of Mexico, Gulf of America, and using that pressure to drive turbines as a way, where those are significantly overpressured. But in normally pressured geothermal reservoirs, most of the energy is locked in terms of heat. We played with a couple of box models. One was kind of a steady state model that looked at rates out, either in volumes or in masses, mass rates per unit time. And just the fact that a uniform pressure in this box would be drawn down over time. You can represent that behavior by a simple continuity equation that changes in pressure will be driven by rates of fluids removed. You can define it either on a volume basis for this storage coefficient or on a mass basis. And if you look at the amounts of fluid that you remove, then if you need to know what the stiffness, the compressibilities of the system are, and the compressibilities of rocks are very low, high moduli, low stiffnesses. Water is high modulus, low compressibility, and pressure or vapor in a reservoir is actually, the compressibility is much higher. And so we looked at if we apply 1,000 meters of head to a reservoir and draw down, then you recover roughly 1% of the fluid from that by the compression of the reservoir, and about 1/10 if you evacuate all the void space, if it's 10% porous. And so that gives us some semblance of how much fluid we can create from these. And finally, the model that we used to look at rates of recovery, so we can have a sustainable reservoir, one that depletes pressures only a certain amount and then holds it steady, is in looking at replacing the fluid that's withdrawn at some rate. The pressure in the reservoir still goes down as a uniform magnitude. It's just a box model, but we can characterize that by looking at this time-dependent equation. And just to give the results, we can find an inflection point at which time it will reach a steady state if we're injecting it some replenishment rate and recovering at a production rate. These don't have to be the same initially, but ultimately they will if they reach steady state. And at that steady state, we reach that at a given time, characteristic time, which we can define as a function of alpha, which we can define in the system, function of compressibility. And we can also define an amount by which the pressure will be drawn down if we're producing at a certain rate and at a storage coefficient of the reservoir. So we can define both of these orders. How long does it take to get to steady state, after which the pressure won't go down anymore, and how much lower is that pressure that started out? If we define that in terms of a flow rate, we can substitute this for Darcy's law. Written in terms of pressures. And if you substitute that in, that gives us this coefficient, links it to reservoir properties and rough areas of flow that we could imagine getting, and lengths of the boxes to be able to actually turn it into something useful. So that's where we left it last time. The next thing that we talked about, so the other thing that we could use to this, I suppose, is if you knew what these pressure drawdowns would be, what you could do is you could think about a non-uniform box system where the pressures are merely changed uniformly, and draw a flow net. And we know that if you draw a flow net between different locations, with, as you know, equipotentials defining the flows between them. I suppose we also know that you can define the volumetric flow rate as equal to the number of flow channels divided by the number of drops. These would be drop 1, drop 2, flow channel 1, flow channel 2, etc. And multiplied through by hydraulic conductivity and delta H. This is for fluid flow. We know that permeabilities are related to hydraulic conductivities through this. And we know that heads are related to pressures over unit weights. And so there's no reason why we can't substitute these. And this is just then becomes a geometric correction that if we know what the throughput is coming into and out of this box model, all we're doing is we're replacing it with volume rate in and volume rate out. These would be, I guess, Q's in this particular case. And so we can convert it into that. We know what the pressure drop would be across the system, and so we know the delta H between inlet and outlet. We know how long it took to get there. If it takes only a couple of months to get there, and this is the way it is for 30 years, then it'd be a good model to use. If it takes 30 years to get to steady state, then perhaps isn't a very good model for that. And so we could replace what we did with a box model with something which has a dimension to it. This is a 2D model, I guess, right? 2D model. So the other thing that we're talking about is whether we could use a more sophisticated 2D model. And we started explaining what that would be last time. This would be our, if fluid is going out, so it has to be going out and being re-injected, so it'd be the red ones. If the pressure is drawn down at the production well and goes up at the re-injection well, we can take a slice of this system. That slice really represents the box that we had before, but now within this slice, instead of being constant pressure over everything, it now is a drawdown at the well. And so if we take this, then what we can do is we can do exactly what we did before, and that is we can write a conservation equation. This comes out of a book. It's a Grant Bixley's book, if you want to show it up. And that is that we can write a conservation equation. So this is mass rate in minus mass rate out equals accumulation. And the accumulation would be in the slice. In this case, accumulation is water removed, so it would be kind of the area under this curve that's being removed from the system as a change in pressure multiplied by compressibility. If we substitute the flow velocity into that, we have a continuity equation with Darcy's law in it. This is a diffusion equation. It's different now because it's in these radial coordinates. The flow domain is like a slice of cake, and so as you're going from upstream to downstream, the cross-sectional area of flow is reducing. And so you'd expect that as a cross-sectional area of flow reduces, it has to go faster. If it goes faster, if it was steady state, if this is larger, then the pressure gradient also has to be larger. So this is exactly the form of the pressure gradient you'd expect. Shallow away, where the velocity is small, much steeper close in, where the velocity is much faster. You could surmise that from Darcy's law. So if you substitute into this, you get the continuity equation, you can rearrange it, and you can solve it, and you can define the coefficients that it gets solved for. It defines a hydraulic diffusivity, and so this is, I apologize that we switch units around a lot. This is, we've talked about a thermal diffusivity. Not sure what we called it. Did we call it lambda? which is equal to thermal conductivity divided by density times specific heat capacity. The units are in meters squared per second, or length squared over time. A hydraulic diffusivity is by making the same division. It's dividing the thermal conductivity, the analog would be permeability, with the amount of storage in the system, which would be specific heat capacity and, this is thermal conductivity, this is specific heat capacity, this is the density of the fluid or solid. This is permeability, meters squared, divided by porosity times viscosity, which is Pascal seconds, and multiplied by compressibility, C, which is 1 over pascals. And just by inspection, pascals, 1 over pascals, meters squared, and seconds is meters squared a second. So the fact that these are both diffusivities means that they're the same units. This is a thermal diffusivity. This is a hydraulic diffusivity. But if you solve this partial differential equation, you end up with something that's relatively complex. But I'm going to make my thing less blunt. And you end up with this being a solution. This is a solution to that equation. And what you can see is if you write this out in an alternate form, which I'll try and do down here, is you could write delta P, and if you divide these components on the right-hand side into, let's see, this is volumetric flow rate, this is volumetric flow rate, this is viscosity, this is 4, don't need the 4 pi, but I'll put it in, just ignore it, K H. H is the height of the reservoir in this particular case. And that is equal to some coefficient. This is an exponential integral, EI, and it's multiplied by porosity and viscosity, compressibility, not specific heat capacity, radius squared, and divided through by, don't need the 4, and this is permeability and time. And so if you wanted to check, you could check that the units of this are uniform on both sides. They would be pascals, it would be meters squared meters, just to do one of them. It would be meters, good question, meters cubed per second, and multiplied by Pascal seconds. So pascals go, seconds go, meters cubed go. We could do the same for this. This is compressibility, this is radius, this is viscosity, permeability is in meters squared. And you'd find this is porosity, which is dimensionless, Pascal seconds, 1 over pascals, length squared, time. You'd find that this is also dimensionless. And so what this is means that this PDE, which has lots of terms in it, actually once you break the terms down, they fit into 2 non-dimensional groups. And so you could describe this behavior by a graph that is in terms of, if this is pi 1 and this is pi group 2, then you could plot pi 1 versus pi 2, and you'd end up with a single curve. You don't know what that curve looks like, but you know if you can solve this, the actual solution is a function of this exponential integral. Doesn't matter what that is. This is the actual solution. It turns out to be a log function, but the important, so you could plot it in log linear space and get a solution. That would be one easy way to do it. The other way is to realize that these two coefficients that we have here are unique dimensionless properties, and if you plot some characteristic of these properties with time, you could fit a unique analytical curve to a non-analytical curve. So in representing this behavior here, you could think of this as a dimensionless pressure, and that's equal to some function of what I'll call a dimensionless time. Right? And that is because if you're doing something to this reservoir, you'd expect the pressure to change over time if you're pumping it out as a constant rate. And you'd expect that change in pressure to look different at different times. It would go from nothing to something. It'd be zero. It actually never reaches an equilibrium. It always keeps on going, which is a little quirk. But each successive time would look like this. So increasing time as you move down curves like this. So in theory, you could draw this curve if you know what this expression is. And so I won't, this isn't in Bixby's book. You could use those coefficients. And the essence of this is to do this. So what you could do is you could calculate, actually you'd do this. So you could plot dimensionless pressure with non-dimensional time. You'll note that these magnitudes, time is in the denominator, pressure is in the numerator. And so this is, actually in this, if the plot would look like this, as we'll look at in a minute, this would be increasing time. Yes, this would be increasing, this is actually 1 over time, as it turns out. And so what you could do is you could take your well data and you could plot it as pressure P minus P0 at a particular radius. So this represents a particular radius, and you could plot it against 1 over time. And so P0 might be here. If time is increasing, then time would be, oops. So if you, before you start pumping, the water level here is at this point here. After some amount of time, which means 1 over time is getting smaller, you end up with different points as the pressure in the reservoir drops. And so if you can overprint this real response in pressure and 1 over time, 1 over seconds, with a analytical solution of the equation which is in dimensionless pressure and dimensionless 1 over time, then you can overlay them. So this happens to be an example that I picked from another text, and this is the relationship of PD versus 1 over TD. There's only one curve because these are dimensionless groups. There's only one solution for every single point on this curve. So this is a unique curve which you don't have to worry about. And if you plot your field data as pressure divided by unit weight, then that gives you an equivalent head in meters. And you plot it against time. So if you plot 1 over TD, then I guess this is time. And so then what you can do is you can overlay these two graphs on top of each other. And if you overlay them so that your data points overlap this. This is changing in gradient, so you have to shift it around until you get an exact fit. And then if you choose what's referred to as a match point. A match point is where you have a convenient value of these dimensionless parameters. So this is 1 over TD. And this other curve was what we call PD, P sub D. On this lower one, that's on this curve. And these are the data on this curve. So change in elevation in the wellbore versus time, you overprint them, and you put a pin through both plots where it's 1, 1 on the analytical plot, and whatever the magnitudes are for the values on the other plot. And those would be, this would be, I don't know, 0.2 meters. And this would be 2 times 10 to the 2 seconds. And so then you go back to the definition of these components, and you know that you need to match these expressions. So this is it. So I guess it's 2.5 times 10 to the 2, 250 seconds, and it's 0.14, not 0.2. And then you can use the values of this parameter here, which, because we've chosen the match point at 1, and we have this value, this will give us the transmissivity. And the transmissivity is equal to the height of the reservoir, h, times its SV. And this is kind of SV. And we know what all these other components are. We know this, we know pi, we know 0.14 meters, we know this well function, and we know the value of the volumetric flow rate, which is defined somewhere else. And we get a magnitude of this transmissivity, which is this. And so this is a function of our reservoir. If we have that, then we can use this expression. This is the transmissivity that goes here. We know from the match point that at 250 seconds we have this. We know we're some distance away from the wellbore, 55 meters, I guess. And this is 4 times the value of u. U is 1.0. And we end up with this value here. This is in units of meters squared per second. This is in units of volume per unit volume. It has no dimensions. It times, yeah, volume per unit. So it's a change in volume per unit volume for a change in elevation head within the system. And so perhaps that's a bit confusing, but because we've used two systems. But the main point to get is that we end up with a conservation equation with Darcy's law in it. We can divide that into the smallest number of free parameters to describe it. That smallest number of free parameters are these 2 pi groups. And if we solve for those 2 pi groups, we get a unique curve in terms of an analytical curve. And if we can fit our data directly on top of that analytical curve, we can look for some kind of match which gives us the characteristics of our reservoir. So that's a typical method that's used in pump test analysis to get parameters for the reservoir. You can use it, of course, the other way around if you have these parameters already to be able to predict exactly what the drawdown of head or pressure would be at any given time. And so in the same way that we did that for a box model, we could calculate how long it would take to get drawn down to this magnitude here. It's a simplified model because here now the reinjection is balanced exactly by withdrawal rate, either as a volume or as a mass. In this case, if we only have material getting taken out, even though the reservoir is infinitely large, or it will never reach steady state. It'll asymptote to a steady state, but it'll never actually reach it, because we're not re-injecting to be able to replenish it. And so you could use this to be able to determine exactly what the steady state behavior of your reservoir would be as it slows to a steady state with time. So maybe that's a bit esoteric, but you have exactly that point here. And these are the commonality between transmissivity is just the conductivity, hydraulic conductivity of the aquifer multiplied by its height, h, and we can define it in terms of this function, and you can get the magnitude of permeability, flow rate, well function 1, pressure drop, height of the well bore, and the viscosity of the fluid. And likewise, you can get the compressibility of the reservoir as a function of this well function, which we know match point was 1, the time at which that match point occurs, the permeability of the reservoir that we've already calculated here and can supply, viscosity of the fluid, and how far that well is away from the production well. So we have a chance of being able to define that. So we did this all on the premise that the power we could get out of the reservoir, the heat rate, heat rate of thermal energy, was a function of the mass rate of flow, specific heat capacity, not compressibility, you know that, which is, I'm going to make this bigger, which is in joules per kilogram per degree Kelvin. It's 4,100 joules per kilogram per degree Kelvin, as you know. I'll make my pen bigger again. And the temperature. So if we can flow fluid through the reservoir sustainably, so we don't deplete the pressure, so we get a reservoir that can continue, either by depleting it volumetrically slowly or by re-injecting somehow, such as with the flow charts. So long as we take care of this, then we could get power out of a reservoir. However, if we don't guarantee that the fluid is coming out hot, then we don't have any thermal energy. And so that's the second one. We have to have both of these. Can't just have one. We have to have both. And so long as our water is our heat transfer fluid, this is always a known quantity, and we have no ability to be able to change that. We could change mass flow rate by stimulating our reservoir or hydraulically fracturing it to increase permeability. We could use another fluid. We could use bigger pressures to drive it across the reservoir faster. So we can do something with this. But we've also got, if we do something with this to increase the flow rate, we've got to preserve the fact that the temperature that comes out of our reservoir is just as hot as it is the same heat. And so what we can do is we could look at a very simple one-dimensional problem. This is kind of drawn backwards. And so in our reservoir, probably we're injecting here with cold fluid into an already hot reservoir. And as we go across the reservoir, that cold fluid will be heated by connection with the reservoir, hopefully to reservoir temperature, and then come out at the recovery well at hot. So that's kind of how this is drawn. However, this analysis is the reverse. And the reverse is if you start off with a cold reservoir and you inject hot fluid in it, it starts off with hot fluid, it goes across a cold reservoir, it takes all the coldness out of the reservoir, changes the temperature of the water into cold water, and you recover cold water. Exactly the same problem, but just backwards. What we want to do is we want to find out when, in this case, we get breakthrough of this case that hot water comes through at the outlet. because that signifies the opposite case for when we get cold water coming through at the outlet going the other way if we're injecting cold water. So bear with me that this is drawn bass ackward. So the point is that there'll be the hot fluid you put into the cold reservoir. It will rob the coldness from this area and pull down the temperature of the fluid, but that cold region, that cold region at the beginning of the inlet will slowly be raised in temperature by the hot water that's dropping its temperature in that zone. So the temperature will rise, but slowly that zone in which it's depleted in coldness, if you like, will transfer towards the right. So we can look at two things. We can look at two fronts. The first front is the advective front. Or the chemical front that I called here. So when you push fluid into this reservoir, the actual molecule of water that you put in at time t0 would have reached this position by the time that you take a snapshot. So this is given by the Darcy volumetric flow rate divided by the cross-sectional area of flow. So this is meters cubed per second. This is meters squared, which is this whole cross-sectional area, and it's divided by the porosity. So the porosity might be 10%, so this means that compared to the Darcy velocity you get going through here, this would transit through the reservoirs 10 times as fast, if this is porosity and if this is about 0.1. And so the molecule that you put in at time 0, at time 10 minutes, would have reached this point. But the rate at which this thermal front will move is dependent on how quickly it can take heat out of the reservoir, take it out of the solid and put it in the liquid, so that it's removed it completely out of the solid and put it in the liquid. And so we can calculate what that is by looking at the two sources of energy that we get out of the system. So the thermal energy injected is going to be the density of fluid, the specific heat capacity of fluid, the volumetric flow rate, meters cubed per second, times the change in temperature it is relative to the baseline, delta T, and over some small time step. So this is the amount of heat energy we put in unit time if it goes in at 100 degrees centigrade and the reservoir is initially at 0 degrees centigrade. This would be 100 degrees. The thermal energy that is removed from the reservoir into the fluid or is absorbed from the fluid is going to be the density and heat capacity of the reservoir, the temperature change, and the velocity of this front moving through the system. So this is moving through here at some V therm. This is how the cold front in the water moves through the reservoir, and it goes a particular distance in delta T, and it's across the whole area of the reservoir. If we equate these, because the heat that goes in from the water and gets pulled out of the water and attached onto the solid, which isn't mobile, they have to be equivalent to each other, and that might allow us to define the location of this point relative to the advective front. We can always know the advective front if we know what the volumetric flow rate is, the area of the reservoir, and the porosity. We don't need to know anything else. So we can calculate what I've called here V chemical. We can get this, but we want to know exactly what this is. So if we equate these, you see all the terms as they are. And if we arrange it, the temperature drop is the same on each side, the time is the same on each side, the area is the same on each side. what we've done is we've replaced this magnitude here with this. And we've realized that we have some terms. The only thing we don't know in this equation is V thermal, how quickly this thermal front is moving through the system. So we can rearrange this equation to solve for that, and we get a ratio of V thermal to the chemical. So if the advective front has gone 1 meter, then the ratio of those two is how far the thermal front has gone, which will lag it. It's always a ratio which is always less than 1. I've done it backwards. So if we rearrange this to get the ratio of these two, if we substitute for the fact that this rho C is equal to that for water, this rho C would be something that would be equal to 1 minus porosity times the specific heat capacity of the rock plus porosity times rho W CW. This would be rho W CW, and it includes this. If you rearrange this, then you have a ratio between these. And so the punchline is, I suppose, that if you look at the converse of this ratio, the reciprocal of it, the ratio of the chemical velocity to the thermal velocity means that if for 10% porosity, if the thermal front is 5 meters ahead in here, the thermal front is only at 1 meter. That's what this physically means. If it's 20% porosity, then if this has gone 5 meters, then this has gone, this has gone 5 meters, this has gone 1 meter, 20%. And if the porosity is 30%, then it's a factor of 2. If it's 100% porosity, then we only have water in here and no solid space, and so they're exactly equivalent to each other. It would be hot water displacing cold water in front of it, and so the same time as the advective flux arrives at this wellbore would be exactly when the temperature changes. And so this is a region where you get this change in temperature across it. And so what you don't want is if you're injecting cold water in here, this would be the arrival of the cold front, because it's inverted. I should draw a better diagram, but I haven't. And so this allows you to calculate exactly when the cold front will arrive at your recovery well, and that may be the end of your reservoir. And so you can calculate that. And so in the same way that when we talked about being able to calculate a time when you will reach steady state in terms of pressures and volumes in the reservoir, this, for instance, tells us when our reservoir might be spent. And that's kind of the essence of this. Is perhaps the key of this class in some respects is that if we want to get the energy out of our system, the rate at which we produce power is a mass flow rate, specific heat capacity, and delta T. And if either of these are large, or if one of them is 0, I guess is another way to say it, then we don't have a productive reservoir. We've spent some time talking about what this first one might be, so now let's talk about the reality of this one. Josh's question in the first week or second week. We can do a simple analysis which allows us to look at this behavior. And so this would be the behavior that if you're looking at the recovery point here, this would be the profile within the reservoir. And so when you start off at time T0, I'll do it in a different color, then your reservoir starts off with a big temperature in it. As you push fluid through it, then you chill the reservoir behind it, but the reservoir would still be hot in front of it. Progressively, you'd further chill your reservoir, but it would still be hot in front of it. So when this particular front breaks through to your recovery well, this is when your reservoir is done. because it's coming through at the same temperature that you're injecting it at. No good. The way that you'd get this to work would be that the characteristic length for thermal conduction within the blocks would be so short that it would give up all of its energy straight away, so that within this part of the reservoir, all this part of the reservoir is turned from 100 degrees centigrade to 0 degrees centigrade. And it's all put in the water, and that water is carrying it downstream. If you have big grains or big blocks, these aren't able to conduct heat into the reservoir into the fluid very quickly, and so you start, as you pass fluid through it, it start off cold. Even though you inject it in at this temperature, it would start off cold immediately it hits the reservoir, and it would build temperature a little bit as it goes across the reservoir, as it takes heat from these big blocks, but not very much. Next, the next scheme would be that it would skim off a bit more heat in the reservoir, and so the heat within this little slither here is analogous to this little slither here. Here it's passing through as a cold front. Here it's just starting off kind of cold and getting also colder and colder and colder with time. And so if at the outlet you plotted out the temperature changing as a function of time, you'd get a graph like this. The right-hand case is the breakthrough of this would occur at some time. That time would be some magnitude. You can calculate what that time would be merely by looking at these two relationships. We talked a bit before about this, but this would be the amount of heat that the fluid can carry with it. It's flowing at a volumetric flow rate Q. It has density and specific heat capacity of the water, and it has a change in temperature that volume of fluid can go through. So that's the amount of heat that's dumped in the fluid. The amount of heat that's pulled out of the rock is given by Fourier's law. The thermal flux is equal to thermal conductivity dt dx. Thermal conductivity of the rock, dt dx. Want to get a volume flux, then you multiply it by area, and this becomes Q. And so this is the amount of heat that you can get out of the system if it's in steady state. And so you can approximate those two values, actually a bit like what we did here. These are velocities, or their mass balances, kind of similar, but not quite the same. And you can define a ratio of these, which is a non-dimensional volumetric flow rate. And what this non-dimensional flow rate would tell you is that if it has a particular value, if it's if the volumetric flow rate is very small, or the spacing between fractures is very small, it would act like this system, and it would behave like this blue line. You get a breakthrough, and you can calculate what that magnitude should be, and it should be roughly a dimensionless time that's given by this, and you could calculate what that magnitude would be. Conversely, if you work with a system which has either a very large flux or what did I say for? So this system will be Q small or S small. They both have to be small for this to be small, and then you'd get this behavior. If converse, so this is conversely, this would be Q large and S large. And if you look at these behaviors, it's predicted by this behavior. If they're both large, then you'd end up coming down like this behavior. And so this means that at the outlet, you start off at a low value here, which you're suggesting here, and progressively it would get lower and lower and lower as you go through here. So in the same way that when we looked at pressures, that we could say when we get a drawdown, and then when we reach steady state, we don't really get a steady state. In this particular case, we can say something about when our reservoir wouldn't become functional anymore, and that would be at this time. And if we know what the values are of these projected flow rates and spacings, then we could say which one of these curves it would be, and we could make a prediction of what that longevity would be, whether it's a day or a year or 100 years, 10 years or 100 years. So we can do that. So we can do a very simple analysis, which I didn't perhaps go through in much detail to be able to do that. If you look at the mechanisms of what's going on, it's kind of embodied in these plots. 15 minutes. And so if you look at a single fracture, that would be a whole bunch of parallel fractures next to each other. So if you have one fracture and then you'd have another fracture here, then by definition the symmetry of this means that this is an insulating boundary, because all the heat at this boundary is either going in this direction to this fracture, or it's going to this direction in this fracture. That means that the change in temperature with direction times thermal conductivity is equal to flow rate. Since the flow rate at this boundary is going equally much in this direction and equally much in this direction, at this boundary the gradient of temperature has to be 0, orthogonal to it by this. Thermal conductivity is not 0 at this boundary because it's a part of a whole system. This acts as an insulating boundary, and therefore the temperature across here has to be 0. So if you drew the temperature across this boundary as it goes into the fracture, then it would look something like this. And if you went into on the other side, so the fact that this is flat here, this is x, this is t, means that this is a no-flow boundary. So, bottom line, too much information. Flowing in a fracture, you can make a line of symmetry here that isolates a fracture on each side from the component behavior. This behavior will repeat in all of these units. If you have water going down the fracture very quickly, then it will be at uniform temperature in the water all the way. There's a high thermal gradient between the rock and the fracture all the way along, and so the flow of heat into that fracture will be equal all the way along, and that behavior will be like this. Conversely, if you have very slow heat along here, this will rob all of the thermal energy from this part of the system. It will take all the thermal energy out of here, it will dump it into the water, and that water will carry it here. Because the water is already at the temperature of the reservoir, there's no impetus for it to draw any more heat out of the reservoir. And so these are the two end members in terms of physically what it would look like in the reservoir. This would have a thin skin of cold rock next to cold water. This one would have an upstream depleted reservoir where the temperature in the reservoir was pulled down to a low temperature, but along the fracture the water here is almost at reservoir temperature, and it would stay at that temperature all the way here. And so you can look at the recovery of heat out of the reservoir you get for these systems. And so these represent the spacing, and I can't see quite what the spacing. The idea is if you have a 1600 1.6 kilometer wide reservoir with 10 fractures in it. No, that's backwards. That's the spacing. One fracture. Yeah, fine. If you have a single fracture in the whole system, you'll draw down the temperature very quickly. So that is this case here. If you have 10 fractures making up that same component, then this is the behavior you'll get. You'll rob temperature from upstream and you'll arrive downstream in years, still hot because you're slowly moving this chilled area progressively through the system. It doesn't feel that chilled area until it actually arrives, and that's what this top line signifies. So having a large number of fractures with relatively small spacing allows your reservoir to act much longer. So that's the heat flow conundrum. It's no different from what we're talking about here, except in real reservoirs there's an additional complication. And that is that if you look at a reservoir that has uniform flow in a whole bunch of fractures, which is what we're representing here, then you get this slow drawdown if you have a lot of fractures compared to a single fracture in this particular case where you're getting this behavior. But if you have fractures which have different widths, then we know that the volumetric flow rate in a fracture equals K squared over 12, 1 over viscosity dP dx. And I guess it would be another aperture for the fracture. So this is the volumetric flow rate that's going through a single fracture. If there's a feedback so that the fracture gets larger as it gets colder, so if you start off with a large fracture that's taking a larger flow rate will make it cool faster. If it cools faster and the rock on either side of it contracts, then the fracture will get bigger. And so if you have larger fractures, there's a positive feedback that if you get large cold flow in a fracture, that fracture will get colder, the walls will contract, the fracture will grow, and it will take more fluid. And so larger fractures become larger, and so the feedback is that the large fractures become dominant and they become cold. So in addition to the fact that if you have just the thermodynamics of the reservoir, if it's a rigid reservoir and nothing is happening to aperture, you'd still get with a single fracture a much faster drawdown. That drawdown is even faster if you have a reservoir which there's a feedback where cold water makes the fractures bigger, they accept more fluid, and therefore they chill more quickly. So this is the behavior if you have homogeneous rigid fractures that don't change in aperture, and if they change in aperture with the feedback, is it will cool down much faster. So you want to be at any particular time at 50 years, you'd much rather be this heat rather than this heat at the outlet. So I'm going to run out of time. So I did some extra work today, and I'm not sure. So there are ways that you can codify this to be able to define exactly this behavior. And again, you can define things into non-dimensional parameters. This represents time out of the reservoir. Actually, this curve here represents this. So this was kind of an arm-waving one based on some zero-dimensional analysis, which is quite useful. If you actually solve the system by putting cold water in, allowing it to run along here, solve for the heat conduction from the block into the fracture, and look at the outlet temperature changing as a function of time, you can get a solution which again gives you a dimensionless temperature at the outlet changing with a dimensionless time. If you have a great reservoir where all the heat is dumped in the fluid because you have lots of fractures, this is the pathway you'd take. You'd get a sudden breakthrough at the end of your reservoir, it would be cold, and you just walk away. If you have a reservoir where you're only getting a little bit of heat transfer into the fluid, then this would be the path that you'd go down. Any particular time, the outlet temperature would be low compared to the inlet temperature, compared to the reservoir temperature. And so this is what you don't want. These are the outlet temperatures. So you can define it in terms of a non-dimensionless temperature between the reservoir temperature and the fluid injection temperature. You can define it in terms of a time, thermal conductivity, densities of the rock, specific heat capacity of the rock, and maybe some characteristic dimension of your reservoir, which is this. And you can define it in terms of a dimensionless flow rate, which is a volumetric flow rate, thermophysical characteristics of the fluid, conductivity of the reservoir, and a characteristic dimension. If you look at real data, so this is an EGS project in the UK from the 1980s, so-called Camborne project, Rosemanose. This is the very first hot dry rock project at Los Alamos National Lab in 1970s. These dimensionless flow rates are something of the order of 10 to the 2 or 10 to the 3, so 100 or 1,000. These are the data that plot on top of those. And so you find that if you look at either of those systems, they plot on a magnitude for something for QD is equal to about somewhere between 100 and 1,000. Has no dimensions because it's a ratio of a bunch of parameters. So if you check through this and put some numbers in for this non-dimensional parameter, we know that to have a viable reservoir, we want 0.1 meters cubed a second, 100 liters a second. We know the definition of density and heat capacity for the fluid. We know the thermal conductivity for the solid, and we can choose a dimension. Let's choose a kilometer. If you put these all together, you end up with a number that comes out of it, which is of the order of 10 to the 2. So this makes sense in terms of actual observed ones. If we could do, if we wanted to, we can check the thermal diffusivity. Note that this is the thermal conductivity of the rock and the storage properties of the fluid, not the thermal conductivity of the rock and the thermal conductivity of and the storage properties of the fluid. We said before that this is equal to 30 meters squared a year. It turns out that this value for the conductivity of the rock and the storage in the fluid is roughly the same as this, because the specific heat capacity of the rock is lower than water and the density of rock is higher than water, so they basically cancel out. But the point is that if you want to, you can define the desired behavior. What we'd like would be to be on this curve. If we choose QD equals 100, which is chosen here, it turns out that these non-dimensional parameters here turn out to be these behaviors in years. 2.7, 27, 270, and 2,700 years. So maybe this isn't ideal. This is 2.7. I don't know. Maybe this is 10 years. Too low, really. But if you look at the magnitude for this value of QD, then these are magnitudes here, and we'd like to be on this curve. And so what we can do is we can evaluate this behavior and these non-dimensional curves if we choose a fracture spacing of 1,000 meters. If we choose a fracture spacing of 1,000 meters, it turns out that the value of QD that we should be on is equal to 10 to the 2. This is 10 to the 0. So 10 to the 2 might look something like this. It's off the plots. And this is exactly the behavior we don't want. Our reservoir would always be cold compared to the reservoir temperature, even from early on. If we reduce the spacing to 10 meters, which is given by some of the dimensionless coefficients. Then the graph, which is equal to 10 to the 2, is this red line curve here. And this is giving the kind of behavior that we'd like to get out of the reservoir. If we reduce the spacing to 1/10 of a meter, so we're going from 10 to 1, we're changing it by 2 orders of magnitude. Again, we're still on this vertical curve, and we can work out what the breakthrough times would be. So all I'm doing, I'm kind of rushing this because we're getting short of time, is trying to make the connection between the characteristics of the reservoir, which are heat transport in the fluid, which has a specific heat capacity of the fluid and the density of the fluid, and thermal conduction from the rock, which has the thermal conductivity of the rock. So the important non-dimensional parameter that controls this is this non-dimensional flow rate. And it makes sense that it's these units. This is how much volumetric flow is coming out of the system. This is how much heat that flow contains in the water that's coming out of the system. And this is how much heat it has robbed by conduction from the rock blocks around it, multiplied by some measure of the characteristic length. If it's a very short characteristic length, it will take the heat very quickly. If it's a very long characteristic length, it'll take a long time for that heat to come out in that balance. And so you could describe this behavior in terms of a non-dimensional drawdown. This would be hot water out, and this would be cold water out. A dimensionless flow rate going through the system. We're right on the money. And also define it in terms of a dimensionless time. Dimensionless time, interestingly, comes out in terms of this thermal diffusivity for the rock. And we said that the thermal diffusivity for the rock, did we call it kappa before? We said this was equal to 30 meters squared a year. But in the same way that we can define behavior for flow within the system, we can also define its thermal longevity. And so the point we're trying to make is exactly, did I write it down somewhere? Is exactly this. What we talked about beginning of today and on Tuesday was making sure that flow rate is maintained through the system. That's not the only parameter we need to take care of. We've got to make sure that it goes in cold and comes out hot, that there's some heat transfer in the system. And understanding that behavior, understanding this equation actually is the baseline of us understanding how geothermal systems work. So that's been perhaps a bit more in depth than I wanted to today, but we needed to do that. Next time, perhaps we'll revisit this next time and go over this a bit more leisurely. We'll talk next time about the other thing that can happen is if you're pouring cold fluids into a hot reservoir, then they're not in equilibrium in terms of the thermal behavior, but they're not in equilibrium in terms of the chemistry. And so you can get chemical deposition, which takes permeability that you might have had, and it may destroy it or may enhance it. And so we need to worry about how we change the permeability in the reservoir as we go across the system. And I will stop right there.